Hi everyone, my name is Jack Koenig. I am a staff engineer at SiFive. My primary job is I work on the open source Chisel hardware description language and Fertile hardware compiler. Both are open source. Today I'm going to talk not about those projects, but more about the general SoC building flow that we're building at SiFive, which we are calling the Federation tools. And so first I will talk a bit about those tools and what they are and how they work. And then I'll go into a bit of a tutorial on how you might use them to onboard a Verilog IP into our SoC generator platform. So I'll start with some motivation. So and some of these slides are taken from previous talks, so I'm sorry if you've seen some of them before. Unsup is a very good slide maker, so I'm borrowing some from him. So first, as we all know, we're all here at the RISC-V Summit for a reason, and part of why RISC-V is taking off is that hardware, compute needs are changing. We have like machine learning is obviously extremely popular. A lot of RISC-V development is around that. And unfortunately, CPUs are not getting faster. So this is a graph of the performance relative to an old VAX processor, and it's a logarithmic scale, and it used to grow logarithmically or exponentially, I should say, and now we're seeing that kind of tapering off. So the way that we deal with this is with custom hardware. So in the machine learning world, especially in like training, GPUs have been king for a little while, but that has obviously changed more recently with custom hardware like the TPU from Google. But unfortunately, the cost to build these chips is really high. So a lot of what I do in my job and a lot of what I'm talking about is how can we lower the cost of developing custom hardware. And the previous tutorial that we saw was about like verification, and that's obviously a really important part of it. You'll see that listed on here as a pretty high cost. But the point is that as technology changes, custom chip costs go up and up and up. So one approach to dealing with this is to copy some success from the software industry. And the software industry is full of open source standards, abstraction, composability, and productivity. Now these are just big terms, but like what are they really about? The idea is you want to make it easier for a small number of people to design something complicated. Right? And so the example that, if any of you have ever seen a Unsup talk before, that he always uses is Instagram. So how did Instagram turn into a billion-dollar company with only 13 people? I mean, how many hardware companies have been billion-dollar companies with 13 people? And according to Unsup's count, a hardware startup needs at least 14 disciplines just to build the chip. Right? You've got your architecture, your logic experts, RTL designers, analog designers, verification, simulation, emulation, if you want to run actual software on your chip. You've got synthesis, place and route, layout, ECOs, of course, foundry experts, packaging and testing of the actual silicon once it comes back. And so, sure, maybe some people can do multiple jobs, but when you're building real complicated chips, you generally have many people in each of these roles. Many people in some, especially in your RTL and your verification teams. But all of this requires a lot of expertise. So how did Instagram do this? Is it just that they are way more productive and way better than hardware engineers? Well, it turns out, as we all know, that there's a whole bunch of stuff out there for them to leverage. I mean, Instagram didn't have to build the language, write all the software. They didn't have to build the chips that they are running their stuff on. They're able to leverage everything beneath them in the stack. And so this is really common in the software world. There's a lot of common open source infrastructure that people use, and then they can build their proprietary thing on top of it. And so what we're proposing at SiFive and others at the RISC-V Summit as well are proposing kind of like open source hardware stacks. So we have RISC-V, obviously. That's why we're all here. At SiFive, we use Chisel as our hardware construction language, which is open source, on top of the Fertile hardware compiler, which is open source. There are open source IPs. We have Rocket Chip and SiFive blocks, and then you can see that there's lots of great stuff from the Pulp guys and many others doing similar types of open source IP. And then in this talk, I'm talking about the Federation tools, which are kind of something to help you stitch all of this stuff together and build a chip. And then, of course, little plug for SiFive, our cloud services are a a product that we're building to help enable chip development. So one of these really important pieces in the software world for anyone who's ever done any web or web development is NPM, the Node Package Manager. So it's a package manager that lets you describe your JavaScript or other language, but primarily JavaScript, piece of work that can be a small or large package, and then it allows you to include it into different projects. And if you look at how many packages there are, you can see that NPM is just blowing everyone else away. But looking at these other ones like Maven, CPAN I think is down there pretty low, but like Maven and some of the others, there are still many, many open source projects that are available that you can then use in order to build whatever you're building. And the point is here that there's millions of users of this, and it enables a really robust ecosystem in the software world. And for those who've been at the summit for the last 3 days, you've seen that there's some amount of this in the hardware world, but I would definitely not say that there's 830,000 examples. I can probably think of tens if you were to ask me to go through what I know of. So what we're trying to do here is we're trying to emulate what software has done and build powerful open source ecosystem. So I said the word federation. What do I mean by federation? It's a suite of open source tools from SiFive that we're using to build our SoCs, trying to build them in a modular way. So what's the vision of what federation enables? So the idea is that you have your IP packages and you have your tools. So an IP package might be something like a UART. It might be something like a CPU core. Whereas a tool might be something like a fuzzer, a RISC-V compliance suite, different tools like that. And so, the idea is that when you want to do some work, you can sit down, you create your workspace with all the tools, with the IP packages that you need and the tools that you need. The tool will analyze everything that you need, pull in everything, including transitive dependencies, which are things depended on by what you depend on. It'll read the descriptions of the IP package and ensure all the assets are there. It'll collect all the commands that are available to you, right? If you include this RISC-V compliance suite tool, then you can say maybe fuzz, V extension or something. So by having that tool in your workspace, you'll be able to use it. And then, of course, you get to the work that you want to do, which is design your SoC. You don't want to worry about all of these things. You just want to get your job done. And so the first tool of the federation tools is called WIT, which is a pun on Git. And you can find it at github.com/SiFive/WIT. And it's a tool for managing dependencies between Git repositories. So importantly, think of it like Git submodules++. For any of you who've done multi-repo management, it can be kind of a pain. And WIT is our answer to that. So it allows us to have more flexible dependencies between repositories while we're doing development across multiple repos. You can think about it as a supplement for Git. It is not a replacement. Git is still the version control system that we use underneath it. And it provides a flexible yet reproducible and deterministic dependency resolution algorithm. So the idea is, if project A depends on project B and project C depends on project A, you can not be stuck with the static dependency from A on B. You can change it to depend on a newer version and do that type of management that for any of you who've used a tool like NPM or Maven in the Java world might be familiar with. But doing this with Git repositories, multi-language, not single language projects. And then it generates a flattened directory structure where we pull in one of each package. And the idea is that it allows multiple developers to develop across multiple repositories at the same time. So for any of you who've done multiple repository development, it can be really painful when you need to change things across two repos and someone else is trying to change things across two repos and you merged in different orders, right? So the idea here is trying to help enable that type of development in an easier way. So, what are the benefits of these small packages? I keep talking about managing lots of repos, and many people are not convinced that this is the right approach. A lot of companies like Google are famous for having a mono repo. Of course, even at Google, for the projects that tend to be more open source collaborative, like Android or Chromium, they tend to live outside of that mono repo, which I think is telling that sometimes you need to be able to split things up. But the idea is that it provides a well-defined interface between the different parts so that you can reuse things in different contexts. So this UART is hopefully abstract enough that you can use it in a small embedded core or in a large SoC, right? That it's not really, and you can use it across different technology libraries. The point here is to build reusable things. It encourages engineers to write unit tests. It's really easy when you have a monolithic code base to just kind of like run everything together. And so the point here is that if something is split up into a smaller piece, then you should be running continuous integration and testing against just that piece. And of course, that type of unit testing, obvious concept, localizes failures, makes it easier to find causes. And a really important thing for us at SiFive is it enables fine-grained access control. So whenever you do a lot of open source development that you're using in your internal code base, if you want to have a two-way street on open source rather than just dumping one way, you need to be using the same open source repo that the open source is using. And so it makes it possible to open source different aspects of what you build while keeping your secret sauce secret. Furthermore, especially in the hardware world, there are issues of export control. And so if you're working in an international community or with people abroad, you need the ability to have fine-grained control over what's accessible there for legal reasons. So it's really important that you can do this type of access control, and a simple way of accomplishing that is with repository level control. Okay, the next tool I'm going to talk about is called Do, I like to point out that this is from the creator of Wavedrom, if any of you have ever used that website to make like little waveforms. Alexi sitting over there. And Do is, like in most Slavic languages means spirit, which some of you may know that's what IPExact I think was called in an early form. But the idea of Do is that it's a manifest document for capturing the intent of your design and how you might integrate it. So you can describe components, designs, configurability of your design. It talks about the important parts for integration, like the ports, the buses, what constraints you have on those parameters, the registers for your memory map. It's open source. It uses JSON 5, which is a bit of an extension on JSON. And it's extensible and generator agnostic. So I'll talk about how we integrate it into our generator, but that doesn't mean, like the whole point is that this should be integratable into others. And so Do is kind of a suite of tools for packaging reusable hardware components. It can import from Verilog. I don't know if the systemRTL and IPExact are fully implemented yet, but the idea is that it can import from all of these formats. It allows you to author, it provides tools to help author, like create the documents, validate them. It can export to Scala and Chisel, which I'll talk a little bit about later, Verilog, IPExact, which is obviously an industry standard that we need to support, as well as documentation. And then eventually, we'll have a GUI to kind of help with some of these things. So what are the benefits of a data format for describing your generators? Well, the idea is that you have one IP package, right? That may be Verilog, it may be Chisel, it may be System Verilog, it may be some other generator, and that you should be able to integrate that into different frameworks. So at SiFive, we have what we're calling the Craft framework, which is Chisel, Fertile, Diplomacy, and TileLink. But for others who may be using Axie or open source Wishbone or more traditional Verilog flow, the point is that these are trying to make these packages usable across these different platforms, not just within our world, but also within yours. And so the idea is that it decouples the design from the underlying IP framework, acting as a single source of truth, because we have found when we onboard IP into our Chisel world, we have to do a whole bunch of work wrapping up this thing, and a lot of it's duplicated information, right? There's information somewhere about the register map, hopefully in a machine-readable format, but frequently in a PDF that someone wrote by hand. And now we have to duplicate that information for our generator so that we can access the memory map. So the point here is we want to keep it dry. There's only one description of the information you're looking for. And that you can then generate whatever assets you need from that. Ideally, this lowers the barrier to entry to adopt your chip design framework. So if a lot of people have built packages that are packaged in this way, and you implement Do, or you implement a Do export to your framework, now all of a sudden you get the benefits of all of those different packages without having to do the work of porting every single one. solving that problem, like yeah. And like I said, if you build something and you want other people to be able to use it, you should not care how they're using it. You just want to provide a mechanism for them to do so. And then the last of the 3 federation tools, so I mentioned wit, do, and now wake, which is a pun on make. It's also a repo on GitHub. And the idea is that wake is a tool and language to make build systems composable. So, well, I'll share that example in a minute. The idea is that using wake, you can define APIs to distinguish the tooling choices from the tool steps. So what do I mean by that? If you look at the software world, it's all built around APIs, right? You can think about, trying to think of a good example, but I'll just go with the implementation of the Java virtual machine, right? There's the open source version and the closed source version, but the idea is that they implement the same API. And so this is something that tends to not be present as often in build systems. In build systems, it's kind of like, the make file describes how to build this and hopefully describes how to build it across different platforms, but frequently might be fairly specific to one. And so what wake is trying to enable is doing software, being able to write your build flow in a software-y way such that you can separate the API from the implementation. And allowing you to plug your packages together without having to change the source to do so. So a little bit more on wake. Some of the features, dependent job execution. So every single job, like whether or not it runs, depends on the result of previous jobs. This is really important for us at SiFive because we have highly parameterized generators, right? From the same generator, we might get a embedded core that that has like a scratch pad, and we need to preload the scratch pad with the test program that we're running and then run it, versus a SoC, a Linux-capable SoC that may have DTS and use standard Linux and be running Linux on top of it, right? And so these are very different, and there are different steps that you will run or not run depending on what you're trying to build. It provides dependency analysis. So if your build is not reproducible, it will let you know that. A lot of modern build tools are doing that, where it's really focusing on separating the user environment from separating the build description from your user environment. It can prune unused dependencies. So you may have to specify your dependencies, but if you over-specify, it actually detects which ones you're using. So next time, if one that you're not using changes, it won't necessarily rerun if it doesn't have to. And generally, you don't need to tell Wake what it built because it's intercepting the system calls for writing files, so it knows what files are output by your job. It provides build introspection so that you can determine what it did. You can query the database to figure out exactly how it got there. So a really neat thing here is, for example, you want to know how a file showed up. You can ask Wake, how did this file show up? And it will tell you the environment it used, the command it ran, and all the arguments to it. And it can even format it as a bash script if you want to rerun it that way. Very useful for debugging when you're trying to write build rules. And it's an intrinsically parallel language. So it's really important, why is make such a weird tool? Why is it that every time I'm trying to remember how to describe something, I have to Google the special variables again to remember which one's which? Well, the point is that what make does that is quite clever and powerful is that it's very parallel, right? It can extract parallelism based, it requires you to write things in a way that it can extract parallelism. So Wake does a similar thing, but using more principled standard programming language techniques rather than kind of a do it once DSL. And that means that only true data dependencies will cause it to sequence jobs. So it will actually check that, if you expect job B to run after job A, you better be feeding the output. This is important for reproducibility. And then a feature that's a work in progress is shared build caching, such that if you've built something once, like if I ran all the regressions, it can record that I already ran them all and save that such that a future job will not have to rerun the regressions. And this may sound a little bit scary, but it proves it based on the hashes of the files of the input, right? So if you have the same input, you should get the same output. Okay, so that part was kind of describing the basic idea of the flow that we're building, and those are all our old slides. And now I'm going to kind of go into kind of a companion to our online tutorial, which the idea being that when you read a tutorial, it frequently is just kind of a description of how you do something. It's like step 1, 2, 3. And I'm hoping that this talk, especially recorded on the internet, will serve as like somewhat of a description of why you're doing some of these things. So first, let's describe our design. We have a PIO block, a parallel IO block. It's very simple. It has an AXI interface, and that's the interface to your SoC. And then on the outside, it has like output enable data and input data. This is just a simple example. And so what we're going to do here is we're going to onboard this. We're going to describe it in a way that can be onboarded onto any SoC platform. But for the purposes of the tutorial, we're using SoC test socket SiFive, which is just a simple, like, kind of like a test harness for IP onboarding. And included with our PIO device, we have a VIP block, which is just going to check, like, it just has a simple function to feed the data back, just to help us check that it's working. This is kind of like the VIP you would have replacing the PHY when you're onboarding like a DDR controller. And then along with SoC test socket SiFive, we have a RISC-V processor, a Rocket processor from Rocketchip. And this will allow us to run C code and actually program our IP. And so my hope is that this tutorial is reproducible. So I'm like including hashes and tags to make sure that if somebody in the future wants to go run this, they can. I'm not doing it live. I don't have enough time for that, but I will go through the different steps. So we use Docker for this. I don't know. Hopefully most of you are familiar with Docker, but it's just lightweight containerization. You can do a similar thing with a virtual machine, but what I really like about Docker is that the Docker file is kind of like, it's a machine-readable, reproducible description of everything you need on your system to run it. So whether or not you use the Docker file, you can look at it and see what you need to apt-get install if you're running on Ubuntu, and what things are being used. And then I'm following the pre-onboarded branch on Block PIO SiFive. So if you're interested in any of this and want to try it out, please check out that README. And you may want to use the Docker file I described to make sure the environment is set up somewhat correctly. Right. And now, there's always a question of, in a tutorial, how much do you go into depth versus how much do you just kind of give a high level? I'm really hoping that this will be runnable by people, so I'm going to go into occasionally excruciating detail just to make sure that you won't run into problems that may occur from weird flukes of the environment. So this command, the sudo docker run, allows you to run a Docker container. Not necessarily on all systems, but on most systems, Docker does require sudo, so this might be something to do on a laptop. But this will, and you don't need to, if you've installed Docker, this command will know to go to Docker Hub and get the container of environment block CI. And then using bash as the shell. There's a minor issue with that Docker container where Python 3.7 was installed but didn't properly replace the Python 3 soft link. So I need to fix that up just to make sure that the pip and Python version are the same. Sorry, maybe not interesting details. And then just for purposes of the tutorial, like I should say that Docker image is intended by use in continuous integration, so like Travis or whatever. And so it runs as a root user, but if you're doing this normally, you would be a user. And so you want to also make sure that we've added a user here. So just some simple commands to create a user, give it a password. I think yes user piping to password is a funny way to do that, but. All right, and then there's a few dependencies that are missing from the Docker container. So in order to run do, we need Node.js. It's written in JavaScript, and so the one thing I do like about the way Node is distributed is they provide Linux agnostic binaries, so you can just curl that binary or that tarball down, unzip it, and you've got an installation on a Linux machine. And then you need to install do using npm. So once we've put Node and npm on the path, we can install it with just npm install. That prefix is just me putting it into a different directory. And then we also need to install wit, which we do just by cloning the Git repo and checking out a stable version, which is, in this case, 0.11.1, and then add them both to the path. So with those steps, now we have the environments to really get started. Oh yes, one other minor setup thing is that because we use a lot of internal repos, we use SSH in our Git remotes, I guess I should say. And so currently, WIT doesn't have a feature to make it easy to switch between them. So if you are doing this tutorial and you don't have an SSH key set up with GitHub, you just need to do that little git config, and it's going to change all SSH repo accesses to HTTPS, which you don't need any authentication for, or you don't need to share a key. And then now for the stuff that's actually in the tutorial that was all set up. So WIT allows you to create a workspace, so you can WIT init the workspace. That -A is like adding a repo. So we're saying we're going to use block PIO SiFive repo, and we're going to get the pre-onboarded branch. And so that's going to clone block PIO SiFive. It's going to read its dependencies and resolve them. So block PIO SiFive depends on lots of different things. This will end up checking out something like 20 to 25 repositories by resolving the transitive dependencies. We then also need to add an environment package. So one of the things I mentioned is reproducibility. If I run something on my laptop, it needs to run on someone else's laptop and run on our compute machines and run in CI. And so we separate the user environment from the system that it's running on. So environment packages are a way of separating that, where the environment package knows how to provide resources like Python or Java or whatever you need. The WIT update here just makes sure that everything is checked out, even though it should already be. And then we do a wake init, which just like sets up the workspace to run. So I mentioned earlier that wake has a database, so it can record everything it's doing. And so this initialization is like creating that database and getting everything ready to go. OK, so I mentioned in IP onboarding, we're using do as a way of describing it. So what we have here in this PIO package, and if you go to the pre-onboarded branch, you'll just see a couple system verilog files. So now we actually need to construct the do document to describe this. So do provides an interactive command line for this. If anyone's used NPM, it's kind of similar to that. So let's go into the block PIO SiFive repo. This is inside the workspace, so it's workspace block PIO SiFive. And then we can do init, and it's going to ask us some questions, like what is the name of the file that we're creating? What is the name of the block? What is the version? Simple stuff like that. What is the type, and what is the source style? So after we've done that, we can take a look at the pio.json5, which is the do file for our block, and we'll see that it has filled some stuff in. It seems that it currently defaults the vendor to SiFive, so if you're not SiFive, you might want to change that. The default library is also blocks, but we'll see in a minute when we have a VIP, we need to change that to VIP. And you can just edit this file. It's just a simple JSON. I'm not sure that this is actually used at the moment, but we will manually record what file sets there are. I suspect that this is something that will be improved as we go. So one thing I want to reiterate is I'm getting into some details here that may not be interesting at the moment, but hopefully for anyone who's actually trying to run through this tutorial, this will provide a lot of useful context. All right, so one of the neat features of do, or of the related do import verilog ports tool, is that it can read your system verilog and record all the ports for you automatically. So that's obviously an important interface in any block. So if we run do import verilog ports, catting the content of the file and reading it into the JSON5, it's going to, if you see there at the bottom, I guess I can kind of point. Yeah, at the bottom there, you can see that it has some ports. There's a lot more than that I can't find on the screen, but just this is what you kind of look for. And so it automatically read all the ports. It has like the widths and the directions. So negative means I think negative means output, but I'd have to check that. And also note that these widths can be parameterized, like this is parameterized by the address width. So I mentioned, and if you see here, for those of you who are familiar with AXI, this kind of looks similar. And so we actually have an AXI 4 Lite interface. So whenever you're connecting this, you want to treat the standard bus, you want to treat it like a bus. You want to be able to tell the generator that this is an AXI 4 Lite bus. And so do provide some standard interfaces. The block arc repo is the description, or it contains all of these. There's quite a few, several AMBA 3, AMBA 4, I believe Tilink and many others are on there. And you can write your own. And pretty neat is that you can infer standard interfaces from the flat list of ports. So most people follow a standard style when they create the ports for one of these interfaces. And so you can use do port inference to infer. So all we do is run that on our JSON file, which has all the ports from the previous step, and we tell it where the buses are, which are located in our do installation. You can provide your own bus descriptions as JSON files, and it will output it back to the same file. And so you'll see something kind of like this. What it has done is this bus interface is saying what it's inferred, and it has inferred an AXI4 Lite interface. However, for anyone who has done any type of machine learning classification, there are others that kind of work but don't work quite right, and so it provides all the alternative things that it found that may be what you actually meant but are less likely. And so of course, if AXI4 Lite's what we're using, it's not surprising that AXI4 was the next interface to show up as a slightly bit less good candidate. And like I mentioned, you can define your own bus interface. And so I've taken the beginning of the AXI4 Lite JSON description, but it's pretty straightforward data description of what the signals are in your bus. And so if you describe your own file like this, then do port inference can infer this bus from the names of the ports and from the directions and styles, including optional ports. Cool. So unfortunately, also for anyone who's done machine learning or anything with inference, you know it only works so well. And if you, for some reason, don't follow the style exactly, you may end up with something missing. So in this case, we have a clock and a reset in. We're not actually paired, and we can add them manually. So this is from the PIO JSON5 file, and I've highlighted in black here the 2 ports that I had to add to the port maps. So whenever it inferred the AXI4 Lite interface, it described T control AR PROT is AR PROT, right? So we have to map a couple extra ports where the left side is the name of the port in the standard interface and the right side is the name in your design. Okay. Another thing that's really important in an AIP is your memory map, right? Like what use is a peripheral if you can't program it? And so in order to add the memory maps, here's a machine readable description of the memory map, right? This is a similar kind of thing that you would have an IP exact. And all you do is make sure to add this to your JSON5 file, and eventually like exporting from IP exact and stuff will work. But for the purposes of this tutorial, we just write it or pretend like we wrote it manually and copy paste it. Okay, now I mentioned the block is parameterized, so do also supports parameters. And so we can add a parameter schema describing what parameters are available in the PIO block. So it has an address width, a data width, a width of the parallel interface on the other side. And then, of course, these have ranges and default values and all that good stuff. Now, that's if you run through those steps, you can look at the JSON5 file that is a sufficient description of the PIO block. And now we need to include our VIP as well. So we have this loopback VIP, which isn't a very complicated verification IP, but it does at least allow us to connect up the backside of the PIO block. So I'm not going to go into any detail here because it's the same basic idea. You initialize the block. This one we're calling loopback. So we're using the loopback system Verilog instead of the PIO, obviously. And the one thing I want to highlight, so it also has parameters, but the important part is that the default is blocks, and we need to make sure we change that to VIP because that affects the package. I keep saying the word package, a very overloaded term, but the Scala package that will be generated later in the tutorial. All right, and so do also has document validation. So this is useful like whenever you need to modify the file to make sure you didn't make a syntactic mistake, or if you accidentally violated a schema when you were trying to map your ports, like maybe you added a port that doesn't exist. So it includes the information about these buses and required an optional field. So if we run do validate on pio.json5, it will succeed and correctly tell us that there's a few ports that we didn't map. But luckily, those are all optional, and we're not using them. We're not using user bits, and we're not using a different clock. So that's what you'd expect to see. OK, so now I'm going to talk about Scala integration of this block. So everything before there should apply to any framework that implements the do document. Now I'm going to get into the more specific stuff that we use at SiFive, which is Scala integration. So do can generate chisel Scala to integrate the IP. We are using this flow to onboard third-party Verilog IP to our generator today. This is what we are actually using. And The idea is that the open source community can use the same flow to integrate with Rocketship. So whenever we onboard things for open source uses, it should be the exact same as what we would use internally for that IP. Now, I mentioned Chisel Scala. Some of you may be familiar with that, some of you may not be. So if you want to learn more about that kind of stuff, you should check out the Chipyard and Firesum tutorial. I don't know how much detail they're going to go into, but it's a longer tutorial, so hopefully more. It's from 1 to 3:45. I believe it's in this room, but you should check the calendar. And I just want to mention that at SiFive, we use Chisel to write our parameterized generators. So the little plug for one of the main things I work on, so please go check it out. And just because I keep saying the word Chisel and the word Scala, what am I talking about? So Scala is a general purpose, object-oriented, and functional programming language that runs on the JVM. It's kind of like better Java with extra paradigms of programming. Chisel is a library embedded in Scala that makes it possible to describe your digital designs in a generator. You're like writing a program to elaborate your design, but it has type safety, semantics, and a compiler underneath it. So anyway, when I keep saying these words, that's all I mean. So now we can generate Scala with do. There's do export Scala, which will generate the wrappers. And by convention, we put these in craft design name source directory. So we can export the PIO block and the loopback block. Ooh, I need to speed up a little bit. So it'll generate .scala file, like name.scala and name-base.scala. The idea here is that the name base should not be manually modified. That's just generated so that as you update your do document, it can update that generation. And you put your modifications into the PIO.scala file. And read more about this on the do Scala repo. Okay, so all of this is a work in progress. Do will generate a lot of what we need, but there's still a little bit that it will not. So it only connects the standard bus interfaces, and we have some other ports that we need to connect. We need to connect the output enable, output data, and input data to our VIP. So in the PIO.scala file, we will import our VIP. Eventually, this type of stuff I think will be generated, but today we have to do this part manually. So we need to import it. We need to define the interface so that in PIO top IO extends bundle. Bundle is kind of like a struct, and it's like a parameterized struct. It has outputs, inputs. We need to actually wire the stuff up. So like I mentioned, do export Scala is only connecting the known buses, and so we need to manually connect the clock and reset, and we need to manually connect to the VIP. And so this code is a bit boilerplatey. Hopefully we can generate it in the near future, but it's not that crazy. We're just materializing these two things called bundle bridges, which are kind of ways of like tunneling ports through module hierarchies. And then inside here at the bottom, we are just connecting the clock and reset to the built-in clocks and reset from Chisel. And then we are connecting the, IO bridge source, I think, is coming from the VIP to the IP that we're onboarding. So the idea here is that this code, though, is not just usable. When I say that we're onboarding this into the test socket, this code right here works no matter what platform we're onboarding it onto. This is like a one-time onboarding cost, and then there's different SoCs that you can onboard this onto for free. Okay, we also need object model metadata. So the object model is just a collection of metadata. It's an important source of design information used by downstream tools, right? Like, what are the features of this design? Does it have virtual memory? What is the address map? What are these things? You may notice that this sounds kind of similar to do documents, and it is, and it's incrementally getting replaced by do documents. So it's like a SiFive internal, it's open source, but primarily SiFive specific design document that we're trying to migrate to the do open standard to make these things more reusable and shared by the open source community. But here, we're just going to describe a simple thing. There's more, like you saw in the do document that there's more parameters than this one, but we're going to just have a width parameter for purposes of the tutorial. And this will, the OMPIO case class is just like is that collection of parameters of only one at the moment, and then the rest of this is instantiating the object model. Similar things that as the tools we're building around do enhance, we can hopefully generate this kind of thing. Okay, we of course need to instantiate and connect the VIP. A little bit more boilerplate here, but basically So in the previous part, I connected things on the DUT side, on the PIO side. And this stuff is more, if you think about like above the PIO block will be instantiated automatically, but the VIP won't. So we have to instantiate it and then make sure everything gets connected together. All right, so that's kind of the Scala boilerplate that you need to use when you're running through this tutorial or when you're onboarding an IP today. And then now we need to integrate it into the build rules. So we have described what we're building, but now we actually have to describe how to build it. And so I mentioned that Wake is the build orchestration tool that we're using for IP onboarding and for building SoCs. And to learn more about Wake specifically, check out the tutorial on the Wake repo. And again, by convention, we're going to put these in build rules/Wake directory. That doesn't really matter. That's just a chosen convention to keep our directory structures clean. And as with anything, we have syntax highlighting for Wake to make it more readable. So if you are reading the code, please use the syntax highlighting. Otherwise, it's hard to tell what's going on. So now we create our Wake build file, and at the top of it, we'll define this block PIO SiFive root. This is really just like a root, it's a directory. So we use, if you look at this part here, this is a string with interpolation, which means like inject a variable. Like if I did 1 + 1, it would run 1 + 1 and then stick it in the string. And so here is a special function in Wake that's like, where does this file live? So if it's a Wake file, it can know its path relative to the workspace root. And so this allows us to just create a stable link to the top of the block PIO SiFive package, wherever it is in the workspace. And then we need to describe the Scala modules. So there's a bunch of Scala code, but it may matter how we build it. Check out the README of API Scala SiFive to learn more about building Scala code with Wake. And so here I have the descriptions for the loopback Scala module and the PIO Scala module. And this may look like there's a lot, and an issue that you may note is that it is technically code, but the idea here is similar to most other build tools. You try to express these things in as data-EA format as you can. So really all we're doing here is we have a name, we have a path to where we keep the source files, we have a Scala version, which we are copying from the SiFive skeleton, which is this package that we're onboarding it onto. We have our dependencies, so the loopback, I'm actually not sure why it depends on SiFive blocks, but I guess it's using something in there. But these are the two other Scala projects that it depends on. And then we just actually create the Scala module with the name, path, and version. We describe where the source files are relative to the root path of the project, which we have to change to source, the default being source main Scala. That's not important convention in the Scala community. We have to tell it what it depends on, and we have to set compile options if they need to change. In this case, we have to set one option because most chisel code follows conventions that require this argument to the Scala compiler. And then it's the same thing for the PIO block, the only difference being it also depends on the loopback Scala module. And that's really it. OK, so we've created our Scala modules, which are kind of like a compilation unit. How do you compile the Scala code into a jar so that we can run it? And then we have a concept of a Scala block, which is really just this Scala module plus a config. So a config is a set of parameters used for RTL generation. This is really important in the chisel world because everything is a parameterized generator, or everything we write is, at least. And so the Scala block is like taking that compiled source code and adding the fact that there's some parameters you're going to associate it with it. And there could be many different parameters that you might use. In this case, we're just using one, the default generated stuff, but the tutorial online includes instructions on how to do different types of configs for different parameterizations of the PIO block. Okay. Now you may need some simulation option hooks. So anyone who's written any language, but especially Verilog and System Verilog, is you might need to provide custom arguments like include directories, defines, plus args that are necessary to compile or run your design. And so this provides a mechanism for declaring those for our loopback and our PIO System Verilog files. I'll note that this uses the publish mechanism of Wake, which is kind of like a way of saying I have something, and then some other piece of the build flow can ask for all published things there. And so this is kind of like telling the whole build, if you are compiling the system.verilog file, this is how you do it, or how you run it as well. In this case, we only have compile options. OK, so we have onboarded our IP, but it's not really onboarded if we can't program it. So we need drivers. So there's a bit of utility for helping generate drivers from the do document. I think that's a long-term work in progress, but it will generate basic drivers for you. For the purposes of this tutorial, with a parameterized module, we have a handwritten one that is more parameterized than the automatically generated ones would be. And so these provide C functions so that you can abstract across the concept of memory map registers, because as we all know, with more complicated things, a simple C function may turn into lots of different register parameterizations, or writes and reads and whatnot. So then we, of course, need to tell the build rules about our drivers. So what's really neat about this is if you're compiling one thing, this isn't that complicated, right? You have your drivers, you compile it with what you're building, and you're done. But the idea here is that we're onboarding this for all whole suite of designs, right? So this PIO block needs to register its drivers such that for any design that has the PIO block, that it will compile the right drivers. So any different framework that you're using this PIO block in will be able to use these drivers when compiling code against the design with that block. And it uses device tree for this. That's, I think, a Linux standard. Forgive me if I'm mistaken. But this is really just a description of what are the drivers, what are they compatible with, and what are the files. And then anything that uses the PIO block will use these drivers. So now we can just write a simple C test. It's when you onboard this block, along with a RISC-V processor, we can run code on it, right? And we can actually check that when we write to the memory mapped registers and read from them, that it does the right thing. And so this is a really simple test. If you look at it, it uses the drivers that we got from the previous step. And all we're going to do is write to bit 0 the value 1 on data enable, and then we're going to check that the result we get back is 1. Well, it's non-zero, but in this case 1. Or no, the result should be 0 because the VIP is exclusive ORing the inputs. So we expect 0. If we don't get 0, then it's an error, and so we return 1. Right? So this is a very simple C test. You can imagine much more sophisticated ones. And we, of course, need to tell the build rules how to compile the test. That test we just saw is pretty simple, just needs the driver. But other ones may have flags, C flags, assembler flags, all kinds of things. Now, for reusability, we try to make this machine agnostic, but there is a filter function for if certain tests are only applicable on certain platforms. In this case, it's all RISC-V, so I'm not, well, I guess you may have things that may require the vector ISA or something. And we can use this to create a test program plan, and the full tutorial will describe how to do much more complicated programs. Like that was a simple one for purposes of the example, but if you wanted to compile the measles of computing, as Professor Patterson put it, Drystone, you also have instructions on the tutorial for compiling Drystone. And so this is, for simple things that don't have complicated compilation instructions, you can just kind of do a small thing describing what files are involved. All right, so let's see, I'm getting there, and there will be a little bit of time for questions. So now we need to create a skeleton DUT. So what is a DUT? It's really a collection of source files and metadata that describes a design, which is a very simplistic way to put it. But in this onboarding platform, we're building these with Rocketship-based generators. So Rocketship is an open source repo that can generate RISC-V. I don't want to quite go all the way to SoCs, but kind of like tiles, including caches and connections to your interconnect, among many other things. And let's see. So the SoC test socket SiFive provides a simpler type of DUT. So the Rocketship version has like everything you might need to describe, and then of course for a simple example where we're going to have a simulation UART, so we can print things to the screen in our seed tests, and a test finisher so that we can indicate when the test is done. We have this test socket SoC, which is just like a very simple design. And so here we describe, That's not good. OK, there we go. I hope y'all can see that again. Cool, all right. So anyway, here we can describe a DUT, which is just, we're just like, the make test socket DUT is really like, you can think about it as a utility function, right? There are more advanced things, there's a lot more that you can do, but for purposes of simple examples, why have all that cruft when you can build abstractions to make it simpler? And so this now describes our DUT. So now we have a full description of something that can be compiled. It has drivers, we can compile software for it, we can run tests on it. So now we need to make sure that our test is actually published and available. So we have that simple demo test from earlier, and that was just how do we compile that C code. But if we're going to run the test, an actual test, not just compiling C, I'm getting gestured too. Oh. OK, cool. Sorry. Well, hopefully this is a little better. So earlier, when I talked about the C code and how to compile it, that's just compilation of C code, right? That's a very generic thing. But if you actually want to run a test, there's more stuff you may need, right? You may have plus args to your design, right? Because this is Verilog after all at the end of the day. And so here's where we can describe like additional information for the full test socket, like when we're running a test that we have a timeout for a number of cycles. We have a random seed for any randomization. There isn't much here. Verbose mode is going to have it print a instruction trace. And so now that we've published this test, so we took our C code that uses our drivers, and we now are wrapping it up such that we have a test that actually applies to different designs. And the neat thing about this is that it similarly has a filter function, so you should be able to write tests that apply to any suite of generated designs where the test applies, right? So if I onboard a PCIe block, then any device using that PCIe will have the associated tests automatically applied to it. And similarly with this PIO block, I don't know how many designs are actually going to instantiate this, but they would get the same tests. And then, of course, you want to be able to run the tests. And so, I'll go a little quickly here, but run sim is like a utility function to help you run it. And so when I run sim on that PIO DUT I created before, it's going to find, well, first of all, it's going to generate the design, because we described the whole DUT, including the SoC test socket with the RISC-V processor, the VIP, the simulated UART, and all the devices that are necessary. It'll generate all of that, will give us Verilog. It's going to compile all the software, the RISC-V software needed to compile tests for it, including the drivers. It's going to, well, I should say compile, it will compile the RISC-V toolchain if necessary, or usually you'll provide that. It will compile the drivers and software to run on the DUT, including, like I said, the drivers and the C tests. And then it will actually run all tests that apply to the design. If you follow this tutorial, there is only one, but you could easily add more, and it will run all of these tests by default with Verilator, and then RunSim with provides a way to change between VCS, Verilator, and Xilium, as well as using generating waves if you want to debug. So all these instructions are on the repo. And then the last part that I knew I wouldn't have time to get into, but I have a slide on, is generating documentation. So it's great that you created this block, but if I'm selling a product that includes the block, I also have to document that it exists, right? If it's not in the documentation, how can anyone know that it's there? And so we also have this tool called Scribble, which is a framework for parameterized documentation generation, right? I'm sure everyone is familiar with some amount of parameterization because you definitely need to change like the base address. But Scribble is a bit more extensible than that, allowing like quite a bit of flexibility for different parameterizations of your design. It will include the register map, whatever details you find appropriate. And the idea here is that if you've onboarded an IP and you've written your Scribble snippets, then anybody onboarding that block will then have that documentation available for their own documentation generation as well. Oh, and of course, the hardware interface needs to be documented too. And so that's it. I have a few minutes for questions. And yeah, please check out the repo and give those tutorial a try. Thanks.
if you want to adopt this flow for other IPs, right? So is your tools, we can go in and modify your tools or something that?
I'm sorry, can you say the last part again?
Can we go to modify your tool chains and or scripting, things like that? Is a source code we can change?
I'm not sure if I completely understand, but I'll try. I think, yes, there are other IPs that we've onboarded, and whenever the flow needs modification, it's all open source code, and so when we need to add additional functionality and stuff, we do. And so, when there are things that we can't handle, the idea is that this flow is extensible or being made more extensible to support that kind of thing. I hope that answered the question.